Hi, I'm Bianca Coker from Region 10, and in this video we're going to look at a set of 3 of our new math standards in 6th grade, 6, 7, B, C, and D. Now, they're not exactly the same, but they kind of support each other, so I thought I'd put them all together in this one video. These are part of the standards in the expressions, equations, and relationships strand that we have now with our new standards. Now let's look at 6.7b first. 6.7b states, the student applies mathematical process standards to develop concepts of expressions and equations. The student is expected to distinguish between expressions and equations verbally, numerically, and algebraically. All right, what does that mean? I focused in on that distinguish between expressions and equations piece. And I'm going to look at that a little bit more detail. However, remember that all these videos that we're making here at Region 10 are our ideas of what we think the standard means. In a couple of years, as we've had some release tests, we'll know a little bit more about exactly what they were intending. But I think I'm onto something here, so I'm going to share it with you. This means 2 things to me. First, it means distinguish representations of expressions from representations of equations. And the reason why I say this, even though the standard doesn't exactly word it that way, is our students really struggle. They're always trying to solve expressions or simplify. Well, they do simplify 2 sides of the equation, but it doesn't work. And so I actually have to spend time with 8th and 9th grade students talking to them about the difference between an expression and an equation. And I've used some things like it's like an incomplete sentence. An expression is like an incomplete sentence. And the punctuation in a sentence is a period or question mark or exclamation mark. Well, the punctuation sort of in a mathematical sentence is that equal sign. So if it doesn't have an equal sign, it's not an equation. It's just an expression. And I can't tell you what x equals in an expression. I've got to have a full equation to do that. So if we're talking about that, an example might be the sum of 2 and 3. That would be an expression. Or the sum of 2 and 3 is 5. We need that verb is to complete this mathematical sentence to make it into an equation. So when I'm translating the verbal expressions into mathematical representation or mathematical expressions, I don't have an equation unless I have a complete sentence. So that verb we're looking for equations are is, was, are, those kinds of be verbs that will help make this into a complete both sentence but also a mathematical sentence or equation. So that's one way I think, even if the standard isn't intending that, that's something we have to address all the time with our students. Now, the other way of thinking about this might be distinguishing between representations of different expressions or different equations. So that's the second interpretation we might have from that. For example, we might ask, are 2x plus 3 and 4x plus 3 minus 2x the same or different expressions? Do they represent the same quantities? So that would be the other way of thinking about 6.7b. Now, the reason why I added the other 2 standards in with this is the way we verify whether or not those are equivalent expressions is what's happening in 6.7c and d. So let's look at 6.7c. 6.7c states, the student applies mathematical process standards to develop concepts of expressions and equations. The student is expected to determine if 2 expressions are equivalent using concrete models, pictorial models, and algebraic representations. Okay, so here's the way they distinguish between 2 expressions. So that's why I think these 2 really go together. So let's look at that look at an example here. In this example, we're trying to determine if the expression on one side of the line is equivalent to the expression on the other side of the line. Now, we've used algebra tiles here. These algebra tiles actually represent 2x plus 3 on one side of the line, and on the other side of the line, it's 4x plus 3 ones minus 2x, or plus negative 2x. In fact, this is what the representation would look like. So when we're looking at this, we're saying are these two expressions, 2x plus 3 and 4x plus 3 minus 2x, the same or different expressions? So what we're really asking, and it's really important for the students to do this, with this concrete model, are these the same quantity? Well, hopefully, when you introduced algebra tiles with your students, you talked about zero pairs. And zero pairs are when we have a positive and a negative value, or opposites that combine together are zero. For example, -1 plus +1 is 0. And so when we look at the zero pairs and simplify that right side expression, that right side algebra tiles set that we built, we'll see our 2 zero pairs go away, and it's very obvious to your students that 2x plus 3 is exactly the same value as 4x plus 3 minus 2x, and they've just proven it. Remember our process standards. We want our students to be able to analyze and justify. And here's a perfect example of how students can justify that these two expressions are equivalent. All right? Now let's look at our next standard, 6.7d. 6.7d states, the student applies mathematical process standards to develop concepts of expressions and equations. The student is expected to generate equivalent expressions using properties of operations. The inverse property, identity property, commutative property, associative property, and distributive property. All right, so this is included in this set because what we do when we say here's a zero pair and we take it away and we combine like terms and all of that, all the things we do algebraically and even with our algebra tiles to simplify are reliant on these properties. So it's something they've actually seen before. They talk about the commutative, associative, and distributive properties in 3rd grade now with the new standards. So they will come to you with this knowledge, especially using concrete models. Now, whether they can spell the words or whether their vocabulary is really sharp on this, that's something that we need to work on, but that it doesn't mean they don't understand the concepts. They do understand the concepts. We just need to remind them of them when they come to us now in 6th grade. So looking at the properties of operations, let's first look at the inverse property. Now this is kind of an interesting property, but it's something that's very critical when we solve equations. The inverse property is basically the property that says to undo an operation, we apply its inverse. And when we're solving an equation, what we really want to do is undo things till we isolate our x, right? Our unknown amount. So we have to know what our inverse operations are to be able to undo them. So what's the inverse operation of addition? It's subtraction. And in fact, our students see inverse operations of those as well as for multiplication and division when they're in elementary school because they do things called fact families. And that means they look at 6 plus 7 is 13, so they know, even without really understanding subtraction, that if I have 13 minus 6, it's that other number, 7. So they learn these fact families based on the inverse operations. They've already seen it. Now the one operation they really haven't done a whole lot of in elementary, and they're going to start doing now with you, are exponents and roots. And so for the most part, those are the only operations that we're looking at doing and undoing in middle school. All right, so now let's look at our properties. The identity property, now there's actually two of these. There's the identity property for addition and the identity property for multiplication. And what this really is I do something to my value and it doesn't change its identity or its value. So if I add 0 to something, I don't change it. I always like to say, okay, I'm going to give everybody in the class $0. Has it changed how much money you have? Absolutely not. It doesn't change anything. Sounds real good, but we haven't changed anything. The identity property for multiplication is multiplying by 1. And we use this all the time when we're simplifying fractions or reducing fractions. When we're coming up with common denominators, we multiply by a quantity of 1 because we know when we take something and multiply it by 1, we don't change its value. It's still the same value. Now notice I wrote this a little bit technically, perhaps. We want to get our students used to seeing things written technically. So the way of saying the identity property, and I would definitely say it in in their words, in student-friendly language. But I would also start getting them used to saying A plus 0 equals A for all real numbers A. That means this property is true for all real numbers. And in middle school until we get to 8th grade, we're mainly dealing with real numbers. So for any real number, I can add 0 and I don't change its quantity, and I can multiply it by 1 and I don't change its quantity. It's still the same, and we've been using that, and now here's the property that says why. An example, 3 plus 0 simplifies as 3, and as we write 1a, you know, students have problems with that. They always want to say 1x. Well, we just call it x, right? We don't say, well, I might say I have 1 apple pie, but I can also say I have an apple pie, right? So this is something we want to get our students used to, and it's just a custom that we have that we don't actually say 1a, we say an a, because multiplying by 1 doesn't change the quantity. All right. The next property, is the commutative property. That's right. We have A plus B equals B plus A. That means it doesn't matter the order in which we add things together, it still comes out to be the same answer. Now notice we also have a commutative property of multiplication. It doesn't matter the order in which we multiply two numbers, we still get the same answer. 2 plus 3 is the same as 3 plus 2. 2 times 3 is the same as 3 times 2. And it's really interesting. When they're learning their multiplication tables, they don't realize that once they know half the multiplication chart, they already know the other half because of the commutative property. But it's really hard to convince a third grader of that. So you have fun with that one. Now, again, the example. Let's take it up a notch. 3 plus x is the same as x plus 3. Sometimes when we're simplifying, things are not in the order we like to see them. And our custom is to have the x's or the variables first and the numbers follow, or the constant terms follow. Is it wrong if they put 3 plus x? Absolutely not. But sometimes it makes sense for us to rearrange some numbers in our calculations to either make the further calculations more simple or to match our custom. In the same way, we could have the quantity x plus 2 multiplied by 2, but we can also bring that factor of 2 out to the front of the parentheses, and that's something we see more commonly when we talk about the distributive property. Students need to know how to interchange these to make their life more simple, and that's what math is all about, simplifying their life, not making it more difficult. All right, one more property to go, and that is two more, but the associative property also has two versions. We have our addition version, A plus the quantity B plus C is the same as A and B added together first and then added to C. Remember what our parentheses do. It tells us what to do first. So we can either add B and C together first, or we can add A and B together first, but either way we go, we get the same answer. And that same property applies to multiplication. We can combine B and C together first and take that product and multiply it by A, or we can take the product of A and B and then multiply it by C. Either way we go, we'll get the same answer. So for all real numbers A, B, and C, this is true. We want to get our students again used to saying these things. And here's an example. 3 plus the quantity 4 plus 2. Well, I would add 4 and 2 together first and get 6. Then I add it to 3 and I get 9. It's the same as if I added 3 and 4 together first and got 7, then added 2, I still get 9. Now, if your students are at this stage, they can look at this symbolic representation and understand it. But suppose they're not. That's when you get out those algebra tiles and you show them an example. Here's an associative property of multiplication. And I'm going to show you how to do this with algebra tiles so that your students can justify their thinking using concrete models. All right, so this bar represents n. We need 4n because that's the quantity we're multiplying together first, so I'll build 4 bars. Now, 2 sets of 4n means I'm going to have 2 of these. So here's our other stack of 4n. Together, I have 1, 2, 3, 4, 5, 6, 7, 8, n. Now, is that the same as saying 2 times 4, which is 8n? Well, yes, it is. So a lot of times, our students come to us with very concrete understandings of things. We need to tap into that concrete understanding and then bring them to our symbolic representations that we are so comfortable with. So Get those algebra tiles out, get those manipulatives out. It's really going to help your students understand the concepts and remember them. All right, one more property to go, finally. The distributive property, the hardest one for all the students to get. In fact, they still struggle with this. And I tell them, and it's true, on every test they'll have from now through calculus, there's going to be a distributive property on there, and they're going to hopefully not get it wrong, because that'll make all the other things they know worthless if they get that distributive property wrong. So it's really important to teach it well. Now, again, they've looked at it in 3rd grade. So we are just building on their prior knowledge and taking them forward into this more symbolic representation. The distributive property states that a value, say A, times the sum of two numbers can be the same as, or is the same as, multiplying that A times each of the quantities and then adding the numbers together. And this is true for all real numbers A, B, and C. All right, let's look at some examples. In our first example, we have the quantity 3 times x plus 1, which is our traditional looking distributive property. So we're going to build this with algebra tiles. First, I'm going to build the x plus 1, what's in the parentheses. So I'm going to use my x bar and my 1 tile. So these together represent x plus 1. Now the 3 in front means 3 sets of, right? That's what multiplication means. 3 sets of x plus 1. So what do you think that's going to look like? I'm going to build another set and one more. Now I have 3 sets of x plus 1. Now that's the same as I had multiplied 3 times x plus 3 times 1, because I end up with 3x plus 3. Same thing's true when we have negatives, same thing's true when we have subtractions. We really need to build these concepts concretely and let our students use those concrete models as long as they need it, while we're gradually pushing them, transitioning towards either pictorial models and then symbolic representations. But I can guarantee you, you're going to lose a lot of them if you start symbolically and stay symbolically. They really need to spend some time with these concrete models. All right, that's all we have time for. Thank you for listening and have a great day.